Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Waves! I'm a-waving at you, wave, wave, wave. All right, today we're going to talk about the big topic of waves. Now, when you think about waves, most people think of like the ocean, right? The ocean is waves. Maybe you caught some waves, right? And water waves are waves, right? Well, it turns out that we need to define what a wave is. It's this: a disturbance in a medium. What? What the heck does that mean? So a medium is typically a solid, a liquid, or a gas. You know this. When you drop a rock in the water, it creates a wave, and the medium is liquid. But I can actually create waves if I like pound on a piece of metal, right? Or there's waves in gas. The fact that you're actually hearing sound from my voice, that's a sound wave, and it's being propagated through air. And waves have different frequencies. Waves have different amplitudes. They have different periods. You see, I can talk like this, and that's one frequency. Or I could talk like this, and that's another frequency. And what I'm doing is I'm changing the wavelength, the period of the wave, and it's going to propagate different. So you're hearing it in sound, but if I was to talk like this underwater, because it's a liquid, things would be different. So that said, there's really three main types of waves. I'm going to talk about two of them in this video. The first one is transverse waves. Here's how a transverse wave looks. So in a transverse wave, the wave moves perpendicular to the movement of the hand. So watch as I move my hand and what happens to the wave. Now, so notice that if I do this, I move my hand back and forth, and the wave is moving. The actual wave is moving off in this forward direction. It's a transverse wave. In this case, the wave now think about a wave. It's actually moving, right? And like with the slinky, it's moving back and forth and back and forth. And it's moving perpendicular. We have essentially a 90-degree angle. It looks kind of like a sine wave, doesn't it? When you have that's what a transverse wave does. The opposite, or the other kind, I guess, is called a longitudinal wave. And it's basically the same thing, except that we don't use the word perpendicular, but parallel. And we can illustrate that also with our slinky. In a longitudinal wave, the wave goes parallel to the motion of the hand. So I'm going to move my hand now forward, and it's kind of like a compression wave. So if I push this, do you see how the wave moves in this direction? I move my hand this way, and it moves that way. Now keep in mind that it's not moving. The metal really isn't moving. It's the wave that's moving off in this direction, regardless of whether it's a longitudinal or a transverse wave. So two main types of waves. There's a third one we're going to talk a little bit later called a standing wave. But we've got transverse and longitudinal waves. They still follow the rules of oscillating motion. They have periods and whatnot. But let's next diagram what that might look like. So in your notes, I want you to sketch a wave. And this would be a transverse wave. We want to label some parts. This right here is called a trough. And this is a trough. This is called a crest. Think about it from what? The crest is you crest a wave, the top of the wave. The trough is the bottom of the wave. Makes sense, total, right? And we can also measure the height of the wave. And that's called A, which is the amplitude. Now think about this for a moment. Amplitude, you might have heard the word amplify or amplifier. When we talk about sound, amplitude is talking louder or talking softer. So amplitude is the height of the wave. I'm not changing my pitch, all right? Because we can also measure how long a wave is. And a long wave is when you go through one cycle from a trough to a trough, or from a crest to a crest. And this is called the wave length. Now in science land, we it's going to be so many meters long, right? We actually give a symbol for that. It's the Greek letter lambda is the symbol for the wavelength. Now, waves are moving, so we have a direction. Let's say it's moving to the left to the right, and it's moving with a particular speed, a particular velocity. Now, mathematically, we've got some equation. We've got velocity, lambda, but it's also like the period, right? The period is how long it takes to go through one cycle, right? That's t. So what you can say is that the velocity is equal to lambda over the time, or the period, right? So the velocity of the wave, how fast it's traveling, is lambda over t. Now you can rearrange and solve for t or lambda or whatever it might be, but these are some equations. As we're looking at waves, and even if it's a different kind of wave, this equation still applies. They move at a particular speed, and they have this particular lambda. You can also say, by the way, of course, is you could also realize that frequency is related, right? Frequency, when we talk about sound, has to do with pitch. So you can also say V is equal to lambda times F, where F is the frequency, because F is 1 over T, right, if I'm replacing. So these are a couple of equations that will help you significantly as we're working through problems with waves. Now, something interesting happens is that when you're in different mediums, the speed of the wave changes. One we keep talking about is sound. So sound travels at 343 meters a second in air. All right, so this is in air. However, in what you call it, liquid water, whatever I think, that liquid stuff, it's 1,500 meters per second. Interesting, right? So air, so you're hearing my voice through air right now, and if you hear it through water, it's going to go like 4 or 5 times faster, much, much faster. And it turns out, I don't know the exact number, but I would do at V in steel. So in some metal, it would be even faster yet. So it has to do with so why does that happen, by the way? It's because, I guess, the molecules are more further apart, and the wave, in a gas than it is in a solid and a liquid, the waves are easier to propagate through harder substances. I mean, think about this from a perspective. You've heard like whales making sounds and talking to their whale friends, and they can hear each other a lot further away because it's traveling so much faster than us who are hearing it through air. I think it's fascinating to think about how this all works. But in general, what's the rule, right? And I've got this in the notes. The stiffer the medium, the faster the wave, right? That's true not just with sound waves, it's true with water waves, it's true, well, water waves is a water wave, I guess, but any type of a wave that we're talking about, the stiffer the medium, the faster the wave will be. So I want you to think about a wave as like energy moving through a medium. It's not like in a water wave, the water doesn't really move, right? I mean, it goes up and down, right, if you're looking at the ocean, but the water itself doesn't actually move. It's energy that's moving through the medium. Does that make sense? And so let's talk what happens to the energy as it flows through 2 different types of scenarios. So sometimes you've got what we call a rigid surface, all right? So let's just take a string, all right? Put a string on here, and I'm going to introduce a wave. And the wave's going to look like this. So it's moving in this direction, and it's going to hit a stiff. So the string is tied very tightly to this, to a wall or something like that, right? But it's going to hit this wall. What happens? But a wave is different than an object. When an object hits the wall, there's momentum and collisions, and we've learned about that before, but a wave just keeps moving on through. And so how does that work? Watch this happen. So if it hits this on a rigid surface, it's actually going to look like this. I didn't draw that very well, but it's going to come back. It's going to come here, whoop. So when it hits that rigid surface, it's going to propagate back on the opposite direction. Now that's if it's a rigid object, but when you have a non-rigid object, so let's say we have a rope that's like, just a loose hoop, if you will. Same ball game, I do this, but now it hits the hoop, moving in this direction. Something fascinating happens when it comes here, is it comes back on the same side. So if it's a rigid, this is rigid. So a string on a rigid versus a string on a non-rigid surface, the wave will continue to travel back and forth. It's reflecting, actually. So waves can reflect. You know that because you're looking at light. Light reflects, light's a wave, and it reflects off of mirrors and stuff like that. And so it comes back opposite. It's kind of weird. So waves move, right? But when they move and when they collide with things, they don't do the things that we learned about when we studied kinetics. We said that they're moving and they collide and they crash and they do things. No, the wave just keeps going. And next up, we're going to talk about what happens when like a wave meets a wave. Some interesting things happen. Stay tuned, because Houston, we got no problems. We'll see you in class.